All right, so hey everyone, I'm Barry. Start with a quick about me. I'm a software engineer at Jump Trading, which is a research and technology-driven trading firm. We have offices all over the globe. It's a really cool place to work, as you can tell by the fact that I'm very nearly a teenager there. I've been involved with C++ standardization since 2016. I've been involved with a lot of stuff that's made it into the last several standards. Most recently, reflection, which is what I'm excited to talk to you all about here today. Outside of that, I have a blog where I write about all sorts of kind of random things that interest me. You may have seen some of my answers on StackOverflow over the years. And as obsessive as I am about C++, I'm also pretty obsessive about swimming. So I also write for SwimSwam, which is a premier swimming media company in the world. So yeah, so this talk has an origin story. And that is a colleague of mine a few months ago suggested that I check out this talk, Practical Guide to Applying Data-Oriented Design by Andrew Kelly. Andrew is the creator of the Zig programming language. And it was a really good talk with a lot of useful content. Even if, like me, you don't know any Zig at all, would suggest checking it out. But in particular, it had this one slide where he's talking about using memory efficiently, and he makes this one-line code change where he's switching a data structure from being an array of structs to a struct-of-arrays. And that's all he had to do in his code. There's no like other weird macro stuff going on here. There's no shenanigans, just the library knows how to do struct-of-arrays. And this just works, right? He didn't have to do any more work for it. And I thought this was super cool. And this is the kind of thing that I really want reflection for. Every now and then you'll hear someone say something like, well, the goal of reflection is to do enum to string. I find enum to string to be like a very boring example myself. For me, the goal of reflection is to be able to write libraries that are this easy to use, right? Like you don't even think about it. Like, oh, I needed a struct-of-arrays, bam, I have struct-of-arrays. And so after I watched this talk, I was very excited to go and implement this right away. And that's what we're gonna talk about today. So we're gonna walk through how to implement SOA vector in standard C++ 26. And I think that's already pretty cool. But that's not really my goal for this talk. I mean, it's a cool example, but my primary goal is to use SOA vector as a vehicle for teaching you all about reflection. This is a very cool new language feature that's going to change the way that we think about solving problems. And so what I want to do here today is start giving you some exposure to some of these new techniques so that maybe you can become familiar with it, so that maybe you can develop some intuition about how to start solving problems in the future so that you can go on and build very cool libraries yourselves to do things that I don't even think are possible right now. What I'm not going to do in this talk is I'm not really going to talk about data-oriented design. I'm not going to talk about why struct-of-arrays is useful, when you might want to use it, like anything like that. If you want to learn more about data-oriented design, there's this very precocious young engineer named Vittorio who's giving a keynote later this week. Has a lot of good content in it. I highly recommend checking you out. Although now he's all grown up, so he looks like that. He's sitting in the front row over there. So we're going to start with storage, right? Like the whole point of struct-of-arrays is to store things. How do we do that properly? So this talk is going to focus around this type square. It's a very simple type. There's nothing particularly interesting about it. It happens to have a lot of internal padding, so it might be the kind of type that you'd want to use struct-of-arrays with. And so if we had a vector, that storage would look like this, right? We'd have a pointer to square, and that's where all our squares are stored contiguously, and we'd have our size and capacity. But we don't want to do that, right? We want to do struct-of-arrays. And so one way to do that is just to turn every member into a vector of that type, right? We have this very simple transformation from t to vector of t, and we're going to preserve all the names, right? And this is one way to do it. It's pretty straightforward, and it's easy to see how we could implement all sorts of other operations on vector, right? How do you do pushback? Well, I push back the x onto my x vector, I push back the y onto my y vector, and then I'm done, right? Now, importantly, some of you might be thinking that this isn't quite right. I'm not going to deal with exception safety in this talk. Like, what happens if like the X pushback succeeds, but the Y pushback throws? Whatever. We're not going to deal with that. Like, pretend that that's not an issue. And so this is fine. This would work. This would solve the problem. But I don't super like this solution, right? Because like, what can we say about these two vectors, right? They're not really independent. They're always going to have the same size. They're always going to have the same capacity. So at the very least, okay, we're storing our size and capacity n times instead of once, which is kind of wasteful. But then it's like, okay, if I'm going to check to see if I need to allocate when I push back the x, and if I don't, well, I don't need to allocate for any other of the members, but I'm going to check that every time anyway. So that's, it's wasteful. So I'm I'm not trying for the purpose of this talk to produce like the most optimal, highly performant thing, but I don't want to prematurely pessimize either, and it's more interesting to produce a solution that's more along the lines of what you'd actually want to write. So instead of doing it this way, we're going to do all the management ourselves. Right. So it's still like kind of a simple transformation now from T. We have a pointer to T for every member, and we're just going to keep the size and capacity ourselves separately. So cool. So how do we actually do this for an arbitrary T? So C++26 has one code generation mechanism in it. It's very narrow. All we can do is, given an incomplete type, we can populate it with a specific set of non-static data members. That's it. But that one little thing is enough to solve a wide variety of problems. And hopefully eventually we'll get a lot more useful, more generic things. And so the way that works is we declare an incomplete type. We have a const eval block, which is another new C++26 feature. So this is a way of having arbitrary code run in a declaration context. And eventually we're going to call define aggregate, passing a reflection representing that incomplete type. And this whole process will complete that type with the data members that we provide. So one thing I also want to point out is you might notice that I'm qualifying std vector, I'm qualifying std meta info, but I'm not qualifying define aggregate. Now, this function is really std meta define aggregate, but I don't need to qualify it because we say that reflections have std meta as their associated namespace, and so ADL will kick in and all of this will just work. And I'm going to be very careful for the purposes of this talk throughout all my slides to qualify the things that need qualifying and to not qualify the things that don't need qualifying, right? So there's no magic using namespace anywhere here. Now, maybe you might prefer to qualify it, that's on you, but I'm not going to. That's okay. So now what we need to do next is we need to loop over all of our non-static data members. And to do that, non-static data members takes two parameters. It takes the reflection of the type, and it takes this very long thing, which is the access context. One of the issues we had to deal with reflection is like, how does reflection cooperate with access control, right? Do you get the private members? Do you not get the private members? And the solution that we have is you actually provide an access context which tells you which members you want. So I can use unchecked to say I want all the members. I can use unprivileged to give me whatever members I have access to in the spot of code I am right now. But for the purpose of this talk, we want unchecked all the time. This is very verbose. So we're just going to pretend that I have some global variable somewhere named context, which is unchecked, because I always want all the members. And now this actually fits on one line, which is nice. And so for every member, we're going to push back a data member spec. And this is now how we define our data member description for each member that we're trying to populate. And that takes the type that I need and the name of the member. So this right here would just be identity. I'm just copying the type and the name of the member. And of course, I wanted to add a pointer. And so we have a type trait for that, right? We have std add pointer is a type trait that we've had for a long time. And one of the things we did is we added a const eval function version of every type trait. And so add pointer is just a function that takes an info and returns an info, and it applies that transformation internally. Right? So now I've built up all of the members from T. I've copied them over. I've added a pointer to each one. And I need to add my size and capacity. So those are just fixed. Those are size T's. And then I'm done. I call define aggregate. That completes the type. And so now I can just use it as if I handwrote all of this. So this is the pattern. We declare an incomplete type. We have a const eval block that does whatever it needs to do. It eventually will call define aggregate to complete that type. And now I can just use it as if I wrote it myself. Right? And so this is, I think, pretty straightforward as far as code concerned, right? Like there's not really a lot of tricks or shenanigans going on. However, it's not quite right as a solution, because you imagine, like, what if I tried to use a type like this? I have struct C and I have a member named size underscore. Well, what's going to happen? Well, like I'm trying to add a member named size underscore in this loop, and then I'm trying to add a member named size underscore out here. And it turns out that you can't have two members named size underscore in the same type. Reflection is not going to change that. This isn't going to work. So what do we do about that? Well, like, as a library author, I can just say, like, well, look, you just cannot have a type with members named size underscore capacity underscore. Those are reserved for the implementation. That feels really user hostile, especially because there's actually no reason that I need this restriction at all. Just because I want these members doesn't mean that I have to generate all the members. Like, I can just pull them out of this const eval block and stick them on the outside, right? Like, we can just do it the normal way, and that just works. And now I don't have any additional restrictions on the type. This additionally has some nice properties because now all of my members are pointers. So for one thing, I can give this type a more meaningful name than storage. They're my pointers. For another thing, now I can more clearly express that the way that I'm computing pointers is just a simple transformation of all the data. So I'm going to just prematurely generalize this a bit, maybe foreshadowing that I might use this function again in the future. And so what I'm going to do is I'm just going to take my transformation, which is std meta add pointer, which now needs to be qualified. And I'm just going to pass this through to views transform, and that's like the transformation that I'm applying to every type of the member, right? So transformed is going to give me a range of data member descriptions where all the names are the same as the original type, and I'm applying some transformation to each type. All right, so I can do it this way. So this returns me a transform view, and that works fine for define aggregate, which can take accept any range. A different way that I might write it is actually like this. We can take advantage of the fact that reflection is a monotype design. Std meta info can represent anything. It can represent a non-static data member, or it can represent a data member description. And so since I have this one-to-one relationship between the original data members and the ones I'm generating, I can just mutate my vector in place and return it like this. For those of you who might be familiar with range v3, you might recognize this as actions transform compared to views transform. And I suspect that it's possible that reflection might drive use of actions more as a pretty good way to solve a lot of reflection problems. So let's talk about constraints, right? Because it turns out that like you can't do an SOA vector on any type at all. There are some requirements that we do need to impose. And these are basically the three, right? Like, what do I need to do in the implementation? I need to be able to destructure your value, and because I need to store all the members separately, and that definitely needs to be independently destructurable. Like, if I take apart your type and then you deallocate memory in your destructor, like that's not going to work. I need to restructure the values because eventually you're going to want to get values out of this SOA vector, so I need to be able to produce them somehow. And I need to put names to storage, right? And so what I mean by restructuring is like all I have are your members. So the only way for me to put them back together is basically using like listed initialization, so that had better work. And so these constraints are basically the top two push us to requiring that T is an aggregate, and the bottom one is basically that T has no base classes. It's possible to implement this with base classes anyway. That just takes a little bit more work, and so we're just going to pretend it's not possible for today's purposes. Okay, so how do I write this? So these map very directly onto predicates that we can write, right? Is aggregate, we have a type trait for that, and checking if the type has no bases is asking for all the bases and expecting that it's empty, right? So this works. And this is also pretty familiar, right? We've all written type traits, and type traits have to be class templates or variable templates, right? Some kind of template. But in reflection, that's no longer the case anymore. We don't have to make everything a template. And in particular, we can write this as a function, a regular function. And going forward, a lot of these kinds of things are going to be written more as functions, right? You don't need to reach for templates anymore. And so we can just transform that. So instead of std is aggregate v, the variable template, we have is aggregate type, the function. In particular, you'll see that now this ends in underscore type. We did our best to try to preserve all of the names of the type traits exactly, but we ran into a few name clashes. And so the pattern there is all the type traits that start with is, the function equivalent ends in underscore type. So is function type, is aggregate type, is union type, and so forth. But they all exist. But maybe you're thinking, okay, that's cool for is aggregate that the standard library is providing me a function, but what if is aggregate was my type trait, right? The standard library is not going to have a function equivalent of my type trait in the near future, right? So what if all I had was this? Like, how do I implement is aggregate type for my variable template, right? And you might think it's like, okay, well, I know how to do that. I'm just going to instantiate the variable template. I'm going to splice the type to get the type out of it so that this works. But this doesn't work. You cannot, in order to splice something, it needs to be a constant expression, and function parameters are not constants. So this doesn't work. That's not gonna fly. But fear not, like we have a solution for you. So one of the functions in the reflection library is called substitute, which is, I think, sneakily one of the most useful functions in the entire library. And what it lets you do is it takes a reflection of a template, any kind of template, function template, variable template, class template, and a bunch of reflections of arguments, and it does that substitution for you. And so what R here is the reflection representing whatever the substitution of that template is. Right? Now, you can't write that yourself, but what you get back out of it is a reflection. And so we're not really violating any of the kind of rules around functions, right? R is always an info, no matter what type happens to be. And so now that I have this, I know things about R. I know that R represents a context for variable of type bool, and I can get the value out of it with this other function called extract. Right? So this 1-2 pattern of substitute extract comes up a lot in a lot of problems. And one way to think about extract is it's kind of like any cast. Because a reflection is kind of like any. Like it can represent anything. And if you know what it represents, you can pull it out. And if you get it wrong, then it's an error, right? If R represents a variable and the type is int, this is going to fail. This is going to throw an exception. But I know it's bool, so that this works. And indeed, we can kind of generalize this and wrap it around nicely. We can produce an algorithm called pred, which just takes a reflection representing any template and returns back a lambda, which is going to take a bunch of arguments and does the substitute extract dance for you. So this is basically a way of turning any template that you might have into a unary or a binary function that you can use. And then we can implement is aggregate type as just pred of a reflection of is aggregate v, which is, I think, pretty nice. All right, so this substitute extract pattern is pretty common, and we'll see it again a little bit later. So that's cool. Okay, we have our storage, we have our constraint. Now we got to actually add elements, right? It's not a very useful container until then. And so if we go back to Square, if we just have our specific instantiation for Square, how do we do pushback? Right? So first we got to check to see if we need to reallocate. Okay, if we're at capacity, we grow to some new capacity. And then, well, we'll placement new our x onto the slot where the new x goes. We'll placement new our y into its according slot, and then we'll eventually increment the size when we're done, right? And so what's going on here is you can see that. So over here, we're kind of iterating over the members of pointers, and we're doing something for every member of pointers in x. And on this side, these are the types and the members of Square. And so we're iterating over both of our types kind of in parallel to do this kind of thing. Now, we could do this, and placement new is great at all. It's the most generic of the placement news approach, but it turns out we also have a library facility that is a little bit more specific called construct-at, and this will deduce the type for us, so I don't have to repeat it. So it's a little bit nicer in this context, since now I only need the members. I don't also need the types. So okay, so that's what I want to write for Square. How do I do this for a generic type? So the prologue's gonna be the same. I just check my capacity, and then I need to grow, maybe. And the epilogue's the same. Eventually, I'll increment the size. So how do I copy every member into its own slot? How do I do that now? And so I can think of a lot of different ways to do this. And so rather than kind of picking one way to present, I'm just going to present every way I can think of to solve this problem. And then y'all can kind of pick which way you like better. Maybe some ways are more suitable to some problems than others. Okay, so option number one is, so we can start by destructuring pointers and value into a pack. So one of the new C++ 26 features is we can now declare packs inside of structure bindings. And so importantly, so we know that this will work for pointers and value. We know it works for pointers because we constructed it, and we know it works for value because we just required this off the back. And then we know that pointers and mems are packs of the same length, right? They're each one for each member. And so then we can just call construct-at for each pointer member pair and then fold over comma. And so for those of you that have done a lot of metaprogramming in the last few years, this will probably seem very familiar, because the way that you do iteration in C++ is, of course, you fold over a comma, right? Now, for other people, this is a very bizarre way to write a loop, because it's a comma. And so don't worry, we got you covered. So one of the other things that we're adding in C++ 26 is a new kind of loop, which is called an expansion statement. And this loop happens entirely at compile time. And there are several different forms of it, but one of the cool things that you can do with an expansion statement is the variable can be const_expr, right? So you can't have a const_expr loop variable in a for or a while or anything like that, but you can in an expansion statement. And I need this to be const_expr because what I'm doing with it is I'm indexing into a pack, which is also a new C++ 26 feature. So this is the same thing that we saw in the previous option, except now I'm actually doing iteration that looks like iteration instead of comma ... So now, so what's going to go on the other side of the expansion statement, right? So I need the numbers from 0 to n, and so that's views iota is a way of just producing that range. Now that's a little bit verbose, and it's kind of annoying whenever you're writing from 0 to n to have to actually write the 0, and then there are situations when you actually need to be careful to actually have the correctly typed 0. And so another kind of small thing that we're adding into the ranges library is views indices, which handles the 0 for you. So this is basically what range does in Python. You just provide the upper bound. So that's option 2. Option 3, so when some of you might have saw, and it's like, okay, well, I'm iterating over 2 things at the same time. There's an algorithm for that that's called zip. Why don't I just write a zip? So in this case, it's not a range zip. I'm doing a tuple zip over our tuples, because the expansion statement can iterate over every element of a tuple. And so I can just write a tuple zip. This is kind of a simplified implementation that does this sort of package and structured binding stuff, but kind of hides it away in an algorithm. And so I'm returning a tuple of tuples of references into every element. And so now pointer and mem here are references to those sub-objects, and I can directly do the construct that. And it's a little complicated, but it's possible to generalize tuple zip to support any number of arguments and also handle like forwarding references correctly. But in this case, we don't need any of that, so the simple case kind of works. This is I think kind of nice. We can also do a more range-based zip and zip over the non-static data members of each type. So this now requires us to do another class member access, because now instead of having the sub-objects themselves, we have reflections representing the non-static data members, so we need to do the actual access to get to the sub-objects. This const expr here is also a new thing in C++26, because up until now you couldn't actually have const expr structured bindings to begin with, and now you can, because we're splicing pointer and mem, so I need them to be const expr here. Unfortunately, this code requires another feature which we do not have, which is non-translate const expr allocation. So non-static data members of returns a vector, vectors allocate, zip is going to hold on to those vectors, and that internally inside of the expansion statement is going to try to create a const expr variable with that result, and that's just not going to work. You can't have allocation persist yet, unfortunately. But so we do have a workaround for this, and that workaround is called define static array. This is part of a very interesting set of library functions that we're adding into the standard. And so what define static array does is it takes an arbitrary range with some requirements, but it takes an arbitrary range and it promotes that range to static storage as if you had created a static const expr array with those contents, and then it returns you a span into that array. And so now this avoids the issue we just saw because we don't have any allocation anymore. Our span is just pointing into this static array. We don't have any lifetime issues because it's a static array. So this just works. Although you can see that I'm kind of running off the end of my slide here. It's a little wordy. And this seems like kind of like a magic function, right? Like how could you do this? And it turns out that it's actually not very magical. And we're going to take a detour to just implement it ourselves. So in this particular case, because we're implementing std define static array, I'm going to pretend that we're in namespace std. I hope you'll all allow me that. And so what does define static array look like? Well, it takes a range, returns a span of tconst, t being the value type of the range. And we're going to do in 2 steps. First, we're going to do all the work. We're going to create an array of those contents, and we're going to get back a reflection representing that array. Don't worry, I'll show that function in a bit. But array here is a reflection representing a variable. And once we have that, we can extract the contents out of it. So we can extract the pointer from the array, so that gives us our first element. And we can get the length by getting the type of the array and then the extent of that type. This is another type trait that we have for a while, right? So that's how we get the contents. So how do we implement reflect constant array? So this now, it has to return a reflection representing an array. So in order to do that, there needs to be an array. So let's do that. We're going to create a variable template, which I very creatively named the array. So it takes one template parameter, which is the type, and then a bunch of constant template parameters, which are the values. And so there's my array. Like, give me an array of this type with these contents. There you go, right? And so now what reflect constant array needs to do is it needs to lift all of the contents of the range into constant template arguments. But we've already kind of seen how to do that, right? So we're going to start building up our arguments. We're going to start with a reflection of t for the type, and then we're going to loop over all of the elements of the range, and we're going to push back reflect constant of lm. So reflect constant is a function that takes a value and returns a reflection representing that value. Or for class types, reflection representing the template parameter object that would be that value. And now that I have all of my template arguments, I call substitute on the array. Right? And so this is the same 1, 2 substitute extract pair that we saw earlier. Right? I put all of my things into the template arguments, and I substitute it into a suitably shaped template, and I know what that shape is so that I can extract the contents back out in a form that's usable for me. One other thing that I want to point out here that's really nice is that you'll notice that the array takes one type parameter and a bunch of constant parameters, right? So it's a heterogeneous template. And with a lot of metaprogramming techniques, like heterogeneous templates are very difficult to deal with, right? You end up wanting to deal with type lists are a lot easier. And so you end up wanting to contort a lot of the way you do things by like sticking your constants into types so that all you have are types. But with reflection, this isn't a problem. Like we just have, we can have a reflection representing a type, we have a reflection representing a constant. They're all of type info. I just have a vector of info. Heterogeneity is just a non-issue. It's not something we ever have to think about. And so now you just declare your template the way you want your template to be shaped, and you don't have to worry about it, which is really nice. Okay, so now we have a defined static array. So I said that this was a mouthful, and it turns out that like if you want to do something like this, you'll tend to want to reuse these members multiple times. So we can go ahead and stick them into static context where members of SOA vector. And once we give them names, you can see that the zip code looks pretty nice. And indeed, this defined static array non-static data members of pattern comes up a lot. So we can kind of wrap that into like a nicer function called NSDMs of or something. Fields of might also be a good name for this. And so now our zip code looks pretty nice. It looks very similar to the tuple zip case now that we lost the wordiness of the way that we have to do the range zip. And of course, option 5 is instead of doing a zip, we can just loop over the indices that we can get from the members.size and then just like index into the 2 spans in our class member access. This also works. One thing we haven't done yet is grow. So how do we do grow? Well, that's actually turns out to be pretty simple. We iterate over all of our pointers. So and again, it's an expansion statement. We pull out a reference to every one of our pointers, and we're going to grow each pointer independently. This actually doesn't even have to be a separate function template because the body of an expansion statement is a different template instantiation for each member if it has to be. And this is just your basic allocation code, right? We allocate some new thing, we copy the old data into the new data, we destroy the old data, then we deallocate. But of course, we probably don't want to copy because we're done with it, so maybe we want to move. And once you see move destroy in C++26, this is relocate, assuming that persists. And so and now we have a complete solution to adding elements, right? We can add elements into our vector, so that's pretty cool. But it turns out that like, okay, adding elements into a container is cool and all, but like eventually you will want to look at them, perhaps do something with them. And so the simplest thing to do with your elements is to print them. Right? So let's go back to our declaration of SOA vector, where we declared our pointers. And so we're going to add a new type here. I'll call it spans. And just like pointers is a type of pointers to all of our types, a span can be a type of spans to all of our members. And I'm going to make it a const span of each member type. And so for our square, spans will look like this. It'll be a span of char const named x and a span of long const named y. Right? And so we'll get to the implementation in a sec, but the way I might want to use this is like I'll push back a couple elements into my SOA vector, and then I want to print the spans.x, spans.y independently. And I would expect that for x, I'll have e and c in there, and for y, I'll have 4 and 6, right? And so it turns out that actually implementing spans is pretty easy. With the stuff I've shown before, we just unpack our pointers. That gives us all of our pointer members. And then we just need to produce for each pointer a span of the appropriate size, and then put them all together inside of our spans. So that's cool. We got our spans. We got access to them. We can print them. But another thing you might want to print is I want to print just every element independently, or in this case, just the first one. So in order to do that, okay, we can add the index operator, and that looks basically the same as spans. You have to do the same kind of thing. But this is going to give me a square. And my square is not printable. And so I can do that. I can make it printable. I can specialize a formatter for square. I can add a parse. I got a format which can go through and write all my members. And because I want to like print them nicely for debugging purposes, like I want to make sure that I remember to put this question mark over here so that my char is quoted, but not put the question mark over here because long is not debug formatable, so question mark is not an acceptable format specifier. And this is like, I can do this, and I did this, here you go. But like, you have to understand that like I'm lazy, and I don't like writing this stuff, and you don't like writing this stuff. So what I want to do is I just want to slap derive debug in front of this type and have that just work. All right. But it turns out like I can't do this. One, this is like a preprocessor directive, so I don't even know what's going to do to my code. But I can do something very close to this, and I can do this. Right? I can write a new thing called an annotations, another new C++ 26 thing, and I'm going to spell it derive debug for no particular reason. And what I would like to do there is I would like formatter to just recognize this and add a specialization for any type that happens to have this annotation, and then have format just like do the right thing. Right? I would like that, and so that's what we're going to do next. We're gonna implement this, and so none of this is in the standard library. There's no derive debug kind of annotation thing. Has annotation is not also a function that's not in the standard library, but we can write that. And so for derive and debug, there's nothing special here. These are just like tag types that exist purely to be able to have that spelling. Has annotation is a little bit more interesting, right? So we need to write a function that, given a reflection that represents anything, there's a lot of things that you can put annotations on. It could be a non-static data member, it could be a function, it could be a namespace. So whatever it is, we don't know really anything about R. Like, does it have an annotation of this value? And so we can loop over all of the annotations. Annotations of is in the standard library, and we can check to see, okay, if that annotation has type T, then I will also extract the T out of it and check to see if it compares equal to value. And if I find anything, return true, right? And so it turns out we kind of thought that this kind of pattern of looking for a specific annotation of a specific type is going to be something that people write a lot. So there's a dedicated function for this called annotations of with type that will now only return annotations of a specific type. So I don't need that check anymore. But now this extract, like now I'm comparing two T's, right? So I'm writing user defined, like equality operator to do whatever. And you'll note that like I did not actually write a comparison operator for any of these types above, so that's not going to really compile for me right now. So I could do that. I could write a comparison operator, but again, I don't really want to. So we could do this a little bit better by not requiring that on all of our users, and instead of comparing them as T's, I can compare them as reflections. So two reflections compare equal if they're both values and represent the same value, or if they're both objects and represent the same object. And so because we have this requirement that any value that you put into an info has to be usable as a non-type template parameter or constant template parameter, there are already rules around how the language compares those as equal. And so we can just piggyback off of those rules. And so derive is a structural type, kind of trivially because it has no members. And so that comparison just works. All right? And so now we pull out the constant from A, we compare it to a reflect constant, which we've seen before, from value. And so now we're comparing reflections, and this is less code that I have to write, and it's also going to be more efficient, which is nice. Now, some of you might be thinking, and then we can pull out expected. Now, some of you might be thinking that like, come on, this is like obviously an algorithm. Why are you writing like a loop to do this? And you're like, yeah, sure. Like we can write this as any of, which might be a little bit nicer. And we can even write this as contains, which is more specific, which also allows me to not have to like specifically declare this. And so this is I think pretty nice, right? Like, do I have this annotations? We can just do contains, projecting constant of onto every annotation to get that right. Okay, so let's go ahead and implement our formatter now, right? Like we've sufficiently constrained our formatter to only do match the types that have opted into this default behavior. So let's go ahead and do that. So we're going to start by printing the name of the type and an open brace and a close brace at the end. So that'll get us to square, open brace, close brace. And then we're going to go through and we're going to loop over all of our bases. So again, we have to do this define static array thing with the bases of. In this case, my kind of cheating approach of pretending that there's a global context isn't going to work because now I also have this like local context thing. And I'm like, this is kind of a mouthful anyway, so let's just pretend that this is just bases of 2. Naming is hard. And so we're just going to recurse and print every base class. Now for our square type, we don't actually have a base. But if we did have multiple base classes, and in particular, if we had multiple base classes, this would just like print them on top of each other without any delimiter. And so we need to go through and make sure that we like add comma space in between everything. This is like the most boring code in the whole thing, so I'm just going to like immediately take it away so you don't have to look at it. But we're going to remember to like conditionally print the delimiter each time. All right, and then we do the same thing for our non-static data members, which and if I do that, I'll get my E4, which is cool. And so like again, I have this thing where like I don't like this, but we've already seen NSDMs of, so I'm gonna use that again here. But this isn't exactly the format that I wanted for the non-static data members. Like bases don't have names, but members do. So let's go ahead and add those. And so now I'll get x equals e and y equals 4, which is getting to be a pretty nice thing. Now you might see that here I'm using identifier of, but up there I use display string of. Why the difference? Well, so it turns out that names are complicated. And in particular, names of types can be really arbitrarily complicated things, right? Because once you have a type, that type could be a specialization of a class template. Some of those template parameters can be user-defined types. Those types could have arbitrary members in them. And like, how do you represent any of this stuff in any meaningful way to the user? And so we have this general function display string of, which is basically just give me some useful thing, hopefully, Mr. Compiler. Because like we can't really do anything better than that. I'm hoping to eventually develop this into like a more interesting library that might have some options, like do you want the namespaces, whatever. But for now, we just have this function that just give me whatever. But for non-static data members, well, like we know that that name is an identifier, right? And so we have this specific function identifier of, which definitely gives you the identifier that this thing has, right? So like namespaces have identifiers, right? And if it's not something that is known to have a specific identifier, then this fails, right? So in this case, we can rely on identifier to do the right thing, and we need display string of for the type. However, this is not the way I wanted to format this, right? Like I wanted my char to be quoted, and it is not here. And so I might try to put a question mark over there, which will work for the char, but it's not going to work for the long because, again, I can't put the long there. So really, in order to do this right, I have to write this whole other thing to wrap my arbitrary value that I want to format, that check to see if that formatter actually supports question mark, and if it doesn't, then skip the question mark that I'm providing. This really isn't that interesting. But importantly, I'm just going to stick it over here to wrap the eventual thing that I'm formatting, and now I can unconditionally provide the question mark, and now this works, right? And so with that, now I have a complete implementation of my formatter. And if you look at this, like, okay, so there's a lot of new stuff here, right? There's a new kind of loop. There's all these new algorithms going on. I have reflections, I have splicing. But like, there's not a lot of tricks going on here, right? Like, I wanted to format, I wanted to print the name, I wanted to print all the bases, so I'm looping over the bases. I want to print all the members, so I'm looping over the members. It's just like, I'm just writing directly the thing that I wanted to write. And I think that's pretty nice that it ends up looking like this. And with that, all of this works, and it prints the thing I want to work, right? So all I had to do is write, add my annotation onto square with derived debug, and SOA vector works. I can put elements into it. I can take them out. I can print them. This is cool. So the next kind of level up from that is like a more complicated form mutation, right? So it turns out that like, okay, well, what if now I want this to work? Right? I don't just want to pull out a value to look at what it is. I want to be able to write into v of 0. And so how do you do that? Well, it would be cool if we had something like Swift mutating properties. And what I could do is I could unpack all of my pointers. I could produce a new t out of all of those pointers. Then I could yield it back to the caller somehow, and then whatever they do with it, I can destructure back into the elements and write them back through into my pointers, right? This is not a language feature that exists in C++. It's not exist in C++ 26. It would be cool if we had something like this, but we don't, and we may never. So the thing that we can do is we can return a proxy here, and really kind of the only thing we can do here. And so when all you have is a defined aggregate shaped hammer, then every solution kind of gets contorted into looking like a defined aggregate shaped nail. So we're going to add a new type here called proxy. And this is going to be L value references to all of the members. And so when I do that, that gives me this type, right? For square, I have this type proxy. But that's not enough to get the assignment to work, right? Like proxy is not assignable from square. Like that's not going to work. Like what I need to write is this assignment operator that does that assignment, and it would be nice also to have a conversion function. It turns out that that'll probably be useful for one reason or another. But I can't stick this inside a define aggregate. Like, define aggregate only accepts non-static data members. Okay. But that's fine. I don't have to stick it inside a define aggregate, right? So like let me kind of clean this up a little bit. Well, like let me just rename proxy to proxy base. I'll put all my members in there. And then I can have proxy inherit from proxy base and add member functions separately, right? That kind of just works. So let's kind of look at what that assignment operator looks like. Well, I need now proxy base's members, right? So I'm going to unpack proxy base into my refs, and I'm going to unpack value into my members, and I'm going to do the assignment. Again, for now, I'm just going to fold over the comma just for space reasons. Now, it would be nice if structure binding supported this kind of like nested recursion kind of thing, right? Because I have proxy has one sub-object, which is proxy base. Proxy base has all the references I need, so it would be kind of cool if I could like write this, and this would just work. But it turns out actually that the way that structure bindings are specified is that if all of your members are members of the same base class, those are the things that you destructure into. So this just works. And obviously, because all the columns line up perfectly, of course it works, right? And so there's our assignment operator. And the conversion operator basically just looks the same, right? We get the refs and we construct a T out of them. But this still isn't quite right because, okay, of course I want this proxy to be printable in the same way. Unlike square, this one actually has a base. But what ends up happening is now that I changed my mutable index operator to return a proxy, when I print this, like that type is not square anymore, that type is proxy, and that's going to print proxy base, that x equals f dot y equals 3, which is not what anyone wants to see this print, right? Like this is just like complete implementation detail. So how do I fix this? Well, again, when all you have are annotations, the solution is to add more annotations. And so we can add another one. We can add another thing called, like, let's say format as, where format as is just a simple type that has an info parameter. And I'm just going to say that the way I want proxy to be formatted is convert it to T. There are other ways to do this. This was just the simplest way I could think of. And so what we're going to do is we're going to go back to our formatter. And with all the code that we had before, except instead of this being a specialization of formatter, we're going to make this a new class template called derive formatter. And we're going to have formatter just inherit from that one. Except we can check to see what the format as type is. So if we have an annotation of type format as, we're going to pull out that type that the user specified. And if not, we're going to format as the type that it actually is. And then we can change the way that we implement formatter for T to inherit from the formatter that they wanted. Right? So it inherits from format as type of what they provided. And so what this ends up meaning is that for the formatter of square that ends up being generated, we're inheriting from derived formatter of square, like we had before. But formatter for proxy also inherits from derived formatter of square, which means that when we go to format a proxy, that's going to convert into a square on the way into this function. And then this function is just formatting square. So it does all the same code that we had before. And so with that, instead of printing the nonsense that no one wanted to see, we print the stuff that we did want to see. And now we're done. Right? And I think that's pretty cool. And so if we kind of take a step back and kind of think up as like, you know, the sky is opening up ahead of you for like what is now possible, you know, we implemented SOA vector. Like I walked through this const eval defined aggregate pattern for how to do things. We learned how to format an arbitrary type. I showed you the substitute extract pair that ends up being a pretty useful pattern. I talked about how to implement custom type traits, and I even showed you how to implement defined static array, and with lots of other new C++26 features along the way. And it's really like the possibilities are kind of endless for what you can do here. It really changes the scope of there are now like a lot of problems which transition from being like, you know, that's just not possible. Like you can't do that in C++ today. Maybe sometime later to like, you know, I don't know. Maybe maybe one of you will go after this and do something that I don't think is possible right now. And that's what makes it really cool, I think. And so since we actually have a bunch of time left over because I Turns out I speak very quickly. I have some bonus stuff over here, which Vittorio tweeted at me a couple weeks ago. And there's an API that he wants to use for his Struct-of-Arrays implementation, and it's called with. And so what with is going to do, in this version anyway, is it's going to look at the name of this parameter, and it's going to see that, OK, you wanted that x. And so I'm going to iterate over all of my elements, and I'm going to give you all of the x's. And so when I call it with the reference char named x, and I'm incrementing all the x's, that's going to change all the x's. But if I rename this parameter to y, and I ask for all the y's, it's going to give me all the longs, right? And we can do that. I can make this happen. And we can start by writing a function called selected. So again, it's a function, it's not a function template. And it's going to take two reflections. It's going to take a reflection of a function. It's going to take a reflection of a type. And what it's going to give back is a reflection representing an array of all of the associated non-static data members. So for every parameter of that function, it's going to look up a non-static data member of that type with that name, and it's going to do that transformation for each parameter. And if there isn't one, it's going to throw an exception, because that one doesn't exist. And so importantly, we're going to return an array down here. And the reason that we want to return an array down here is then the way that I implement with is I start by calling this function. So I'm passing it for my function the reflection of the call operator of the lambda, and a reflection of pointers, right? Not t, but pointers, because those are the ones I actually want to deal with today. And I'm going to splice that right away. And so that is going to give me an array. Arrays can be decomposed of structure bindings. And so I can declare a context for auto with a pack of my non-static data members. And now I have a pack of all the associated non-static data members for each parameter of the function that is provided to me by the user. And at that point, well, I just loop from I to size, and I call the function with the subset of members in the order that they were asked for. And that's it. That's it. Like it's not actually a very complicated operation once you figure out how to shape it correctly. And so that's this kind of stuff is pretty cool. Like that all of this is possible that didn't used to be before. And obviously this is a pretty nice API. Like there's no other added instrumentation, no macros going on. Things just work. So I hope you found that interesting, and I hope you're all as excited about reflection as I am. I think it's going to really change the way that we think about C++ in the future. So thank you. Yeah, so questions? Yeah.
Thanks for the talk. So I kind of think that we're going to use Struct-of-Arrays. Sorry, I always, need to wrap around my head. So yeah, we need Struct-of-Arrays. So instantly, specifically to support like user-defined types and make the a lot of performance out of it just automatically for the users. I hope. The question that I have is like really minor. When you have like there was a function which of course I forgot the name, which is returned to the identifier as you said, and you said fields like non-static data members have identifiers, namespaces have identifiers. What does it return if you have the namespace alias?
The name of the alias.
The name of the alias. Okay.
Yeah, which is also we know is an identifier because that's the only thing it can be. Yeah.
So this is an amazing talk. Thank you. Say I wanted to write something cool, or at least try to, like you did here. How would I do that? What compiler would I use?
So right now, the most up-to-date implementation is Dan Katz's fork of Clang. It's on Compiler Explorer. Thank you, Matt. And so you can find it in the drop-down menu. We recently renamed it. So it's the one that's labeled Reflection C++ 26. Go try it out. It all works in.
Great, thank you.
Great talk, great choice of photos. And I want to mention two things. First of all,
I love what I'm seeing. I'm really concerned about the compilation times. Have you had any chance to benchmark it or have some sort of metric? So how it scales as you use this?
Yeah, so one thing is, Dan's implementation is the most complete one that we have. And he was not concerned with compile time yet. And what's crazy to me is that he had never touched Clang before doing this. And he's like, oh yeah, my first project, I'm just gonna implement reflection. Sure, that is how things go, right? And so so trying to benchmark it right now is not very meaningful. Marek is implementing this for GCC. He's making really good progress. So that'll be really interesting to see once that becomes more mature. But one thing we've already seen, even with this implementation right now, is that there's a lot of stuff that you can just write. So for instance, if you want to implement variants using define aggregate instead of the recursive union template thing that you have to do right now, the code is a lot simpler and it just works. And so there's a lot of things that implementation will just fall off at some size, and now it just works. So that's already a lot better. But I do expect that it should be really good eventually, especially once people start focusing on that.
Awesome. Second thing I want to ask is, I like the syntax that I see with the with example. One thing that's a bit scary is now even the choice of a name or a parameter can have a significant impact on what it was actually doing. So what are your thoughts on that? Do you feel this is a good use of reflection? Do you feel we're going to see more of this? And is this good for the readability of code in general?
Well, I think as with all things, it depends, right? It is true that you can write code to now depend on things that there's no reason for you to depend on, and people changing random things can break you. That will definitely happen. But on the other hand, there's a lot of things where it's oh no, that's actually what I want. I want people to depend on this, and I want people to single it, right? There's a lot of examples with things I want to do automatic bindings for other languages, and there's okay, well the parameter names are significant, and I could do it that way. If you don't want to depend on that kind of stuff, you could choose to write things differently. You can choose to use something like annotations to drive what names you want to use, and then you're not based on the parameters anymore. And so reflection is the kind of thing that's with great power comes great responsive kind of thing. I can now observe everything about your program, and so technically I can write something that will break anytime you change anything. And it's well, don't do that. But someone's going to, and it's just the way things are.
Makes sense. Thank you.
Yeah.
Hi, thanks for the talk. I was wondering, now that we have this new way of generating code, what sort of debugging tools and how can I look at the generated code essentially for this?
Yeah, so that's a great question. So the only thing that we can do to generate code right now is define aggregate. And so one thing you could do is just write a function that prints out the contents of your type, right? And so that is one thing that I use sometimes when I'm generating types. It's okay, actually print the members that you produce, print their offsets or whatever. I don't know if there's anything better than that around, or if anyone's working on anything better. I don't really have a better answer yet.
First off, amazing talk, as everyone has also said.
Thank you.
I noticed one thing, which was you introduced this new concept of annotations. Is my understanding correct that the reason why you didn't choose, attributes that you can choose any is the whole ignorability of attributes co-couple? And furthermore, are we able to reflect on attributes?
Okay, so no, you cannot reflect on attributes. There is a paper that ends up being complicated for annoying reasons. So yes, partially the answer is yes, we wanted to avoid the whole ignorability thing. But there's actually the bigger problem, which is, so we want these things to be values, proper values. So one of the things that you did not see in my code anywhere where I was using annotations is parsing, right? You just get the value, I use the value, I move on with my life, right? And so we thought that was a very important way to do things. And so in order to get a value, well, okay, well, if we want to use the attribute syntax and you have something like no discard, well, what value is that? And you start thinking about it, it's okay, well, we can contrive a value for these things. We can pretend that okay, maybe there's a magic std adders namespace that is where all of the standard attributes live, and vendors can always do whatever they want with vendor defined attributes. But then well, attribute names don't do lookup. So okay, well now now you start to have to think about it, like, what if someone made a variable like int no discard equals 5, and like right after that used like no discard in square brackets? Like, well, what annotation do you get? Do you get the which value do you get? And it's like awful, right? Like it becomes like all these kind of awkward questions that like no one wants to have to deal with. And so we're like, well, why don't we just like pick something to like make it very clear? And we picked like equals, and it's like kind of ugly maybe. But like, you get over it, and so it's kind of fun.
My second question, I have generally noticed that in constitutive blocks, at least every time that I've tried with EBG's implementation, I will try yours. But I've never been able to successfully introspect the class before it's finalized. And I also find that is a prerequisite for any number of, I would argue, very simple things, such as, I don't know, automatically generating getters and setters for a given class without resorting to different subtleties such as creating a new class and inheriting from it, and so on. Can we currently introspect the class before it's finalized?
So right now you cannot, right? Like right now there are but like you also can't generate the getters and setters either. So yes, like eventually one of the things I want to work on for C++29 is like more proper like code generation mechanisms where you can do that kind of stuff. And once you get there, then it's like, yeah, there's like an endless series of use cases for like, yeah, I need to know what I have so far in my class to know what other stuff I'm going to add as I'm going. And so we'll get there. But right now we're not there. So like we wanted to get something in, so we kind of took the.
We'll get there, that makes me happy.
Yeah. I mean, don't quote me on it, but this isn't being recorded, right? Yeah.
Okay, well, first of all, Barry, thank you for the talk.
Thank you.
I thought it was awesome, but also thank you for all the work on reflection. I don't know if people here are as aware, yes. I think the slides in the description of the talk, maybe you've noticed this if you open the proposal itself, but Barry is one of the people that drove this, and without him, that wouldn't have happened. So I honestly humbled. Second thing I wanted to say that I totally agree with you that reflection is going to give us a lot of interesting library utilities that we can have. And I kind of wondered also about the annotation. Specifically, I wanted to ask you about the annotation. For example, format as. Should we, for example, consider standardizing something like that for if we deliver formatters or deliver users ways to do formatters, which is a utility, I would expect maybe for upcoming proposals to also come with specific annotation for the reflection, for communicating the reflection aspect.
Yeah, so for sure something like just that give me the default member-wise formatting is probably something that should be standardized eventually under some shape or other. And yeah, this definitely changes the way that you want to think about like a lot of things. And so one example.
Properties. It's like a property for. So I think what I'm asking, like maybe when we look at proposals in the standard, we can also look at the annotations that are relevant to it and consider standardizing them so that users can pick those and assign this property for their.
Yeah, so for sure. So like a really good example of that is actually like, so trivial relocation like is a language feature in C++26, but you could implement that as a library in C++26 also, right? Like we need some way to mark a type to opt into something. That's an annotation, so it kind of begs the question of like how we think about doing language features. Like a lot of language features could become library features in the future, and that's really exciting because it turns out that like not everyone can crack open a compiler and implement their idea and get other people to use it, which is even harder. But writing a library that you can post somewhere, that people can try out, that you can get feedback on, that you can iterate on, and that's a much lower hurdle. And then maybe eventually like we get enough experience with that library, and that library should become a new language feature. But now we suddenly have all this experience that we couldn't have gotten before, which is also really cool for me. And we've seen that, by the way, like in Rust, where there have been like numerous language features that have gotten all this experience as like procedural macros and stuff. And so that also gives you confidence that like the language feature is legit, right? Because like, oh yeah, people use this. It's just like, oh, we can make the ergonomics a little bit better, right?
At least from what I've seen, Rust have a worse reflection compared to us so
Yeah.
far. But anyway, last thing I wanted to say is that thank you for opening my mind regarding, I I'm very happy that we picked meta info, single object type, because you really opened my mind in terms of how we can have general algorithms for general types and still have a stormy type language, but have general of the algorithm similar to templates.
Mm-hmm.
So thanks for that.
Hi. As everyone said, awesome talk. Very cool to see a more practical application for the reflection syntax that everyone's been talking about. This is kind of a tangential question, and so I don't know if you're the right person to ask this. But it seems like every time you're at a talk that's like really const expert or const eval heavy, there's always this point where they're like, oh, you want to do this thing, and the code's super obvious, and it's like, oh, wait, that's right. Function parameters are not const expert. And so, like, my question basically, especially for a const eval function, like, it just seems terribly unfortunate that, like, this is not possible. And so my question was, is there this huge rabbit hole underneath this that I just have never been exposed to, and that's why it hasn't been fixed, or is it just nobody's fixed it?
We'd fix what, that parameters aren't constant?
The parameters are not.
So that's like actually pretty fundamental, because like const eval functions are still functions, and so they have to behave like functions. So if you have a function that takes an int, so like a good example I want to use is like, okay, like let's say this function returns like std array of int comma that bound, right? Like I can't have f of 1 and f of 2 return different types now all of a sudden, right? And so it's pretty important for like functions to still behave like functions, and like a lot of stuff actually would totally break down if you kind of remove that. And I think we're a lot, like people get stuck in a lot of ways for two things. Like one, like, well, it's constant, but it's like not constant enough. It's like not like really constant. But then the other thing is like I think a lot of people think of const eval functions as more like macros, where it's like, oh, I just want to like substitute directly into this thing, and it's like, oh, well, if this was a macro, then it would just work. But it is still a function, and so it has all the same kind of rules that functions have. It's just what const eval means is that like it just doesn't get to code gen,
Right.
and so it's a bit of a different model. And I do hope like that eventually we will get like a better macro system as part of like reflection and code generation, and then a lot of the stuff might change again. But like that part right there is like it's pretty fundamental to the way the language works.
Thank you.
And really also like I think this is one of the things that makes a lot of reflection programming difficult. And that you really need to build up intuition and get more experience with is this thing of like, how do I deal with constants and which things can I do where? And this is why like substitute is so handy, because you can get things that aren't constant, lift them to constants and then put them back down. And you can keep like the function interface, which is a lot more convenient for people to use.
Thank you.
Sure.
Yeah, thank you for the great talk. So I have a question. In the initial parts of the slideshow, there was something called the unchecked access context. So is the status quo today like, so for example, let's say I have a class, it has some public members, some private members, someone writes some reflection-based code on that class, also takes the private members into account, and in V2 of the library, let's say I remove those or change those, and their code breaks. Does that tie into the great power, great responsibility situation where they should not have done that?
So there's three contexts that you can use for getting members. You can say unchecked, which is just give me all of them. You can say unprivileged, which is give me only the public ones regardless of where I am. Even if I'm like within the class and I can see the private ones, just only give me the public ones. And there's current, which is give me all the ones that I currently have access to. So this will include things like, oh, I'm in the class, so I have access to privates, like I'm in a function that's a friend, all that kind of stuff. And so which one you want to use like is really situation dependent. There are times when like it only makes sense for you to want the public ones, and you should only iterate the public ones, right? Like if you're generating something like I'm generating like Python bindings for my class, like I'm only going to generate Python bindings for the public functions, right? So you do use unprivileged. But like in my example over here, I wanted to check that you have no base classes, right? So I need to see if you have any base classes at all. I don't care about them. Like I'm never going to like try to access, but there needs to be none. In order for me to check that there are none, I need to like ask for all of them. And which one you should use just depends on the context. Yeah.
Thank you.
Sure.
Hi, thanks for the talk. I have a simple question. In your slides, you have examples where you throw exceptions. Are those runtime exceptions? And if so, can you lift them to compile time errors?
So this right here, this is a compile time exception. And so see, this is another new C++ 26 feature. We can actually now throw exceptions at compile time. We can catch exceptions at compile time. And the rule is that if you don't catch the exception at a compile time, that's a compile error. And so in this case, there's no code that's ever catching this exception. And so so in my example, like I actually typed X and Y correctly, but if I tried to pass a lambda named Z, I would get a compile error at that line somewhere saying that like I would actually like try to provide like a useful message over here, and that is the message that I would get in my compile error, which I think will be pretty user friendly.
And can you then like follow up then, can you control the source location because at that point this would be buried under several levels?
Yeah, so meta exception gets 4 things. It gets a message, it gets a reflection to which thing through, oh sorry, it gets 3 things. A message, which reflection of which thing through, and a source location. And so you can provide whatever you want to provide.
Thank you.
Yeah.
Thank you for Hannah, the second one for.
Very as usual. First of all, I want to say I fully share your vision of a future in which reflection allows us basically to blur the distinction between library features and language features. It would be interesting to see who in the committee handles such features, whether it's OOG or LOOG. And secondly, as to those annotations, how close are they to getting us to full meta classes?
Well, they're not really. So annotations are purely something that you add somewhere that someone else can query later. So they don't really resemble meta functions in that way. Meta classes. So like meta classes was like you do this thing and it like runs code as a consequence of that annotation to do something to your class, right? So it's a much more like an active participant. In this way, they're also very different from like the way that Rust procedural macros work, where like if you put derived debug on your type in Rust, what that does is that is going to emit that like what we would call a specialization, but you know they would emit an implementation of debug for that type, and it would emit all that code on the spot right there. Whereas the way that I did it is very different. Like mine, this is more of a pull model. It's like I'm adding a specialization formatter and it's checking to see it, right? So like annotations are completely pull based versus meta classes are like push, right? It's like do this now, kind of thing.
I don't know, maybe it's like Python places an annotation and it results in having a bunch of stuff added to your class.
Yeah, so that is like one possible direction. Is like what we do is like we add on annotation types, and like if an annotation has like a specific kind of like function named like on complete or something, what that does is after the type is complete, it emits some code or like something else. But like right now, like we don't actually have any other code generation mechanisms, so there's nothing interesting to do there. But eventually, I hope there will be, and at that point we can talk about like what that interface ends up looking like.
We have these annotations or meta classes being the default implementations for concepts, for example.
Sure. Yeah. All right. Thank you.